Okay, let's talk about this. Every second the sea is moving, the ship is rocking and structure is shaking. But how do we even begin to measure or predict what all this motion does to a piece of metal? Excellent question, Anita. All starts with how we translate wave energy into structural response. How are you going to translate the wave energy into structural response? That the bridge between the wave motion and structure motion is the response amplitude operator. So we can say that response amplitude operator that connects between the wave motion and structure motion, or is like a translator between the sea and steel. Exactly, the sea speaks in waves, the steel answers in motion or stress. REO tells us how strong the steel's answer will be for each wave frequency. So let's define it clearly. RO is the ratio between the response amplitude and the input wave amplitude for each frequency. So for each frequency, what is the ratio between the response amplitude of the structure to the input wave amplitude of the sea? So it's like saying, yeah, for every 1 meter of wave height, how much does the structure move? For every 1 meter of wave height, how much structure move? For example, if REO is 0.5, that means structure moves half as much as wave height, and REO equal to 2, that means structure moves twice as much, meaning resonance. So the resonance is when the structure amplifies at certain wave frequencies. Perfect. Each structure has its natural frequency, and when the wave match it, the REO spikes. So visualizing the REO curve. Can we visualize it? Yes. Imagine a curve where the x-axis is the wave frequency and y-axis REO value. So x-axis is the wave frequency and y-axis is the REO value. Okay, that's how you can imagine it. This is the y-axis and this is x-axis. Okay, it usually looks like a bell, a small at low frequencies and peak at resonance, and then drops off. So for a floating body, a low frequency, long waves, the body moves almost with the wave. For near natural frequency, it vibrates, so vibrates more, so REO is greater than 1. At high frequency, the inertia resists fast motion. So low frequency, the body moves almost with wave. At high frequency, inertia resists motion, that's why RO is less. Here RO is greater than 0, so if it is REO is 1 if you take it. This portion is less, this portion is much less, and this portion is more than REO, because at the resonance only more than REO it will go. So at the REO source where the structure is most sensitive. So REO source structure where the structure is most sensitive. It will show where the structure is most sensitive. It's like a tuning curve for the structure. So from REO to stress spectrum. Now that we know how much the structure moves at each frequency, so we know how much the structure moves at each frequency, we can figure out how much stress each motion causes. The wave energy is given by its wave spectrum, which shows how much energy exists at each frequency. So wave energy means the wave spectrum means it will show at each frequency how much wave energy exists. Like saying the sea has many frequencies, small ripples, medium swells, and big slow waves. So S and F tells how strong each one is. So now the stress spectrum is found by combining the wave spectrum with REO. Y square, this square, y square, because energy is proportional to the amplitude square. If the structure responds twice as much, the stress energy becomes 4 times as high. So the stress spectrum tells us how much stress energy at each wave frequency contributes. Beautifully said. Now let's think deeper. Interpreting the stress spectrum. When we look at S sigma F, the peak tells us which wave frequency are most damaging, and the area under the curve gives us total stress variance, and the width of the curve tells us how quickly the stress changes over time. The total stress variance is given by RMS value also, right? So RMS is square root of M naught, that is the area, that's the average strength of the stress fluctuations, and moments like M2 tells us about rate of change, right? Again, so M2 gives us the rate of change. This gives us the information that how fast the stress crosses 0, how quickly it oscillates. So M0 energy, M2 speed of stress changes, both matter for fatigue. So from this stress spectrum to cycle, this is actually TZ is square root of M0 by M0. So TZ is square root of m naught by m0. So now we calculate the mean zero crossing period. It tells us the average time between the peaks in the stress signals. T is if it is so if T is 0.25 second, there are about 4 cycles per second. 1 divided by 0.25, that's 4 cycles per second. So done in 1 hour, 3600 seconds. We get 3600 divided by T is equal 14,400 cycles per hour. In 1 second itself, we are getting 4 cycles. So in 1 hour, 3600 into 4, that's 14,400 cycles per hour. So why Rayleigh distribution? Now we have thousands of stress cycles, but not all are equal. Some are small, some are large, and how do we describe that? That's where Rayleigh distribution comes in. If the stress signal is narrow banded, meaning it's dominated by a small range of frequency. Narrow banded means what? It meaning it's dominated by a small range of frequencies. Then the peak amplitudes follow Rayleigh, and the probability that the stress range amplitude is, this is the probability. So the smaller stress cycles happen more often than big ones less often. Small stress cycles happen more often, big one happens less often. That's why fading is progressive. Most cycles are harmless small ones, but a few big ones cause larger damage. Like most waves are small ripples, but sometimes big rug wave appears. Beautiful analogy. And the beauty of Rayleigh's curve is that it captures the randomness perfectly. Now let's calculate the damage integration. Now we have everything we need to compute the fatigue damage for each small range of stress, sigma to sigma r plus delta r. We can have the number of cycles, so we know the probability and we know the total number of cycles. In the total number of cycles, that particular stress range, how much probability is that going to happen? Maybe, for example, the stress range of 20 MPa could happen, say 10 percentage of probability in out of 14,400, 10 percentage. That's the stress range we can get. Then that particular stress range, how much number of cycles is going to happen? So we can calculate the damage by number of actual number of cycles by our number of cycles for that stress range. So, and integrating over all stress ranges, we can get the damage. That looks complex. Can we solve it? This is a standard Rayleigh integral, and the result is this one, including gamma function. Understanding the gamma function meaning. What is this gamma function? Gamma, it is a gamma function. It's a generalization of factorials. If m equal to 4, then gamma 1 plus m by 2 is 3, so gamma 3 is 2 factorial 2. So mathematically it just wraps up that long integral into just a neat one constant. As physically it accounts for how damage accumulates for all possible stress amplitudes. So the total damage depends on the number of cycles, material constant, slope, and the stress RMS value. Exactly, that's the heart of the fatigue prediction. So what happens when RAO changes? What do we know? So what if we change the RAO curve, say making the structure stiffer? Good question. The stiffer structure usually lowers RA amplitude. At resonance, the peak is smaller. That means less energy in the stress spectrum, smaller m naught, smaller sigma naught, much lower damage. Remember, fatigue damage increases roughly with stress power m. So m equal to 4, then doubling RMS stress means damage by 16 times. So a slight increase in the flexibility can massively reduce life, and this is why designing ROAs properly is crucial in SIP and offshore engineering. Comparing two designs, let's compare two cases. Parameter RAO peak, it's a 2, design A flexible, design B is stiff, and RMS value is 20, and here it's a 12. Slope is same for 4, number of cycles is same. For design A, the damage is proportional to the stress power m, so 20 power 4, so 16,000, 1 lakh and 1 lakh 116,000. For design B, it's a 20,000, so 1 by 8 damage. So the stiff design has only about 1 by 8 damage. So that's the exact RU optimization saves fatigue life. Final summary, we can see the wave spectrum that tells us the energy of waves at each frequency given from the C data. RAO, structure sensitivity to the waves, response by wave amplitude for each frequency. Stress spectrum, stress energy from each frequency, and spectral moments measures the total and rate of stress change. M naught is rate of stress change. RMS is the average stress fluctuations, zero crossing period time between the stress cycles. That is the square root of m naught by m2. Rayleigh distribution probability of stress ranges, Eisenhower materials endurance, damages, accumulated damage. So the travel sees energy travels through audio into the steel vibrates and stresses, and the Rayleigh distribution tells us how those stresses destroyed slowly. So exactly from the ocean's randomness, micro cracks we can now trace every step. That's the essence of spectral fatigue analysis. RAO Rayleigh, two sides of the same coin. One connects waves to stress, other connects stress to probability. Rayleigh connects stress to probability, RAO connects wave to stress. And together they let us predict when the sea will finally make the street whisper enough. So let's see one more. Oh, there's a tiny crack at the corner, but we didn't reach full failure yet. How can it start so soon? That's the nature of fatigue. Even when stresses are below the yield point, the metal remembers every fluctuations. Each stress cycles leave a small scar, invisible at first, until one day all those scars add up and the structure gives up. So metal's memory. And the law that helps us sum up all those memories is called minus rule. So the idea behind minus rule is that minus rule says that each stress cycle consumes a small fraction of life. When all those fractions add up to one, failure occurs. So Ni is the number of cycles experienced at the stress level I, and Ni is the number of cycles of failure at the stress from its curve. So each term is called damage fraction. So it's like saying if a structure lives 1000 cycles at 100 MPa, we use 100 cycles at the level, and we have used up 10% of its life at the stress. Right? If we repeat that at many stress levels, we just keep adding those fractions. When the sum reaches, the structure is exposed to fail. So let's put in words like each stress range takes away a small piece of life. When all that small pieces together equal one life, the structure fails. That's linear damage accumulation, a simple but surprising performance. But what if the material records relaxes between loads? Assumes no recovery, pure addition. A real material sometimes behave differently, but minor rules is still the foundation for the most engineering theory analysis. Connection between minus rule and spectral analysis. Now let's connect it with our earlier spectral method. We have a random stress process full of thousands of stress ranges following a Rayleigh distribution. Thousand stress process. A small stress range contributes a little damage. If we integrate all those, that's the continuous version of minus rule. The spectral fitting formula used earlier is the spectral is simply a spectral form of minus rule. We have replaced this discrete sum with the continuous integral based on the Rayleigh probability. Simple minus rule. This is the stress range, cycle experienced, cycles to failure, damage. So we can calculate the cycle experience and cycles to failure, total damage. 21% of fatigue life has been consumed. When d equal to 1, fatigue is 0.1 after 1 month. We might expect failure after 5 months under similar loading.